In this video, I want to just share with you how I could use Excel, or how you could use Excel to do the calculations that are involved in Chapter 12. In Chapter 12, we're focusing on what we call multinomial distributions, and those distributions involve essentially counting data, so proportions. We are extending what we already know about proportions into this particular field right here. So the first test that we would have done is really testing the equality of proportions. The idea that we will say multiple populations have the same proportion of some parameter that we are interested in. So for example, market share and so on. So we could think about different towns, and if you're a company that's marketing in these different towns, you have the same market share. So market share is a proportion, 38% of the market, 25% of the market, and so on. So if you set this up, you would need to do calculations in terms of your expected frequencies and your chi-squared values. So typically the problem will be presented in the form of a matrix. So I'm going to just show you the matrix data that we have here for this particular problem. This is the problem that I actually solved in one of the videos, but I just want to show you how we use an Excel to assist us with the calculations. All right. So if we go over to this Excel spreadsheet, and I'm making this spreadsheet available to you, you will see how I've sort of, this is a problem about looking at the use of social media by adults in 4 different countries. And is a proportion of adults that use social media the same in the 4 countries. And so we have our data right here for a sample of 3,000 people overall, broken down by country and by whether or not they use the social media platforms. And you could see globally, for when we combine the 4 samples for the US, Russia, China, and the UK, 56% of that sample uses social media, 44% say they don't use social media. So that's our observed frequencies. We now need to calculate the expected frequencies, and the expected frequencies is based on the notion that all the proportions for the different countries are the same. Now, our estimate of what that proportion is really from grouping all of the 4 countries together, and then determine, if you look at that 0.56 over here, that 0.56 is essentially our best estimate of what that proportion should be by pooling all of the 4 samples together. And so now, if you want to determine what you expect if they all had the same proportion, then you would say, okay, 56% of the 800 out of the UK who should say yes. 56% out of the 500 in China should say yes. 56% out of the 700 in Russia should say yes. And 56% out of the 1,000 in the US should also say yes. All right? The numbers are kind of rounded a little bit. You see 559.3, that should be actually 5.6. But what happened is I sort of rounded up my proportions here to 2 decimal places, but that's neither here nor there for now. So what you're seeing is that these are the expected values, and then of course if you take 0.44 and you multiply by these same samples from the different countries, you get the number of people that you expect to not be using social media. All right, and so that gives us our expected frequencies. To do the calculations in a methodical way, you would apply this formula right here. So row total times column total over the total sample size. So for example, for the first case, United Kingdom, yes. So the row that corresponds to that is 1678. The column that corresponds to that is 800. And the overall sample size is 3,000. If you really look at that, what you're seeing is that the 1678 over 3,000 is really just the proportion of people who said yes, 0.56. And when you multiply it by the column total 800, you find what is the number of people in that 800 that actually said yes, right? Oh, that's sorry, that you expect to say yes. Look, The number that actually said yes was 480, but you expect 447.5 to say yes. So what I've done is I've just put in the formula for that. So if you look here, you could see I have my formula, and that formula is essentially this formula right here. All right, row total, column total divided by the overall total. So clearly in the formula we'll have to fix the overall total, since all of them will use that total sample size. But here, since you're getting your row values from here, you're going to have to fix this column G, right, in your formula. And then since you will be getting your column totals here, and you'll be changing the columns, you're going to have to fix the row to whatever that row is, because you're going to move column by column along this row. So in one part of the formula, when you're looking at your column totals, you're going to fix the row. For your row totals, you're going to fix the column. So you could actually see the formula in here where I've done that. And once you calculate one of them, all you have to do is to simply drag and fill. All right, drag and fill it down, and then you will get your expected frequencies. And then you repeat the table, and now I'm going to calculate the portion of the chi-squared value. So if you look at the chi-squared formula, it's Fij minus Eij squared over Eij. So if I take this cell, my Fij is the 480 minus the 447.5. I need to square that. So if you look at my formula up here, if you could see it, I'm squaring that, and I'm going to divide it by this expected value right here. Now this is for this particular part of the calculations. You do not need to fix any rows or columns or any cells, because you have to kind of move with this. When you come to this one, you need to take this value and this value and work with them. When you come here to this third one, you will take this value and this value. So for the portions of the chi-squared value, you do not need to fix anything. All right, so once you do that, you now have your chi-squared values. You could add them all up to give you your overall chi-squared value, which is the value of your test statistic, in this case 79.352 for this problem. And we want to do a couple of things. One is we're given the significance level, so I've set it up there for you. You could just change it depending on whatever significance level you're going to use in the problem. The number of rows, so for this kind of problem, typically there's only 2 rows, because it's a binary situation, either yes or no. So when we're looking at equality of proportions, there's usually never more than 2 rows. All right. So here we go, and the number of rows is 2, number of columns 2. Degrees of freedom is row minus 1 times column minus 1. Since there's always 2 rows, so row minus 1 is always 1. So we could just say that the degrees of freedom is equal to k minus 1, right? Here, degrees of freedom, df equal k minus 1. And what is k? K is actually the number of populations that you have, or the number of columns. All right, so there was actually 4 of them, so 4 minus 1 is 3, so our degrees of freedom is 3. We could use that information to find the critical value, and so here's our critical chi-squared value, and the formula you use for that is chi squared CHISQ dot inverse. So inverse, what happened is we take an inverse of the function. So we were provided with a probability, which is your essentially your significance level alpha, and the degrees of freedom. If you give it that, so you see my C28, which is this value, and my degrees of freedom, which is this value, and it gave me this information here as 7.8147 as the critical value. All right, and then I could find the p-value from Excel. I would use chi-squared distribution, right tail. I want the area in the right tail, so I would provide it with the 79.352, which is the value of my test statistic, and then I will give it the degrees of freedom. degrees of freedom. So if you look at that formula, you will see that G26, that's my value, my test statistic, and then the degrees of freedom is C32 right here. All right. So with those two values, I get the actual p-value. And look at the p-value. It's 4.23 by 10 to the minus 17. It's extremely small. So we know that we're definitely rejecting the null hypothesis here with that. All right. So that's the Excel setup. Now, if you have a different problem and you say you had only three populations, you could just sort of replace those here by zeros and then just work with the three that you have. Put the total values in here, the total values in here, and just put zeros in here. And then you will make the appropriate changes, and over here you should end up getting zeros. But here, because you have to divide by 0, you will end up getting infinity. So you could just delete those values in there so they don't mess things up for you. All right. So, for example, if I just change those to 0, as you can see, right? So that's 0, 0. This should only be 0. So everything here is 0. However, when it comes to this part, those are infinity. So I will just remove that. If I remove that, then it will just add up these values over here for me, those 6 values. All right, and then you could go ahead and calculate your appropriate values. So that's how you would use the template. Even though I've set it up for 4 populations, you could still use it for 3 populations. Or if you now needed to use it for 5 populations, chances are you may not have to deal with 5 populations. But if you had to use it for 5 populations, then just simply add a column, right? Insert. Put your values in here, and then just make sure that you continue the formulas you fill to get the sum over here. Make sure that your sum totals in terms of your row totals will include the new values, and you do exactly the same thing over here, and then you simply copy the formulas across to calculate the parts of the chi-squared value that is missing, and then you will adjust. I don't think you need to change this because this value is referenced in the formula. Even though you moved it over, it will still be referenced by the formulas over here. So you can use that template for 3, 4, 5, however many populations that you have. All right. Now we'll go to this page. This page now allows you to do pairwise comparison. So say you reject your null hypothesis, right? If you reject the null hypothesis, then in that case, you're saying there's a difference between at least one of the proportions is different from the rest. Okay, we don't say all of them are, because remember the null hypothesis states that they're all the same. So all you need is one of them to be different, and you basically will reject the null hypothesis. If you want to know which one is different, you could actually do pairwise comparison and say, okay, let me compare 1 to 2, 1 to 3, 1 to 4, right? 2 to 3, 2 to 4, and then 3 to 4. You could do that in this case. So what we're going to do is we're going to do some pairwise comparisons. This is actually called Marasculio test to determine which proportion or which pairs of proportions actually differ for this data that we actually have. To do that, essentially what you're going to use is the parts of a confidence interval, but that confidence interval is based on the chi-square distribution. All right, I'm going to show that to you in terms of what that looks like. So if we look at this formula over here, that's a confidence interval for the difference between proportions, but it's actually using the chi-square distribution instead of using z like we've done before, where we've used z alpha over 2. We're actually using chi-squared, which is interesting. All right. So if we use that, we could actually get a confidence interval for the difference between the proportions. So technically, we are still dealing with confidence intervals. This is a point estimate plus or minus a margin of error. So this particular test will tell you, take pairs of the proportions and compare them to see if we find a difference between any particular pair, so that we could know which one is kind of out there. All right. What you need to know for this particular test, because what this test actually does, it will compare the absolute value of the difference, which is the point estimate. So it doesn't care if it is a negative or positive. It will compare the absolute value of the difference to the margin of error. It will compare those two. And if the absolute value of the difference is greater than the margin of error, then you will conclude that there's a difference. Now, just to demonstrate that for you, because it's not immediately obvious, is that whenever we're doing a confidence interval for a difference, for us to actually find that there is evidence of a difference, the margin of error must be smaller. In other words, the point estimate, which is the estimated difference, should be larger. The magnitude of that should be larger than the magnitude of the margin of error. So you will conclude that there is a difference if the point estimate is larger than the margin of error. Let me demonstrate it. So here's let's say we have this case right here where the point estimate is 0.15, 15%, and our margin of error is 0.04. So notice our margin of error is smaller, right? If I add and subtract 0.04, I go from 0.11, 11% to 19%. So both of those values are positive. So there is a difference between those two proportions. All right? The sample difference being 15%, I add and subtract 4%, so I go from 11 to 19%. Now look at the next case where the margin of error now is larger, right? So 0.15 plus or minus 0.2. So now I'm going to negative 0.5 to positive 0.35. So it is possible for the difference to be negative. It's possible for the difference to be positive. It's possible for the difference to be 0. 0 is contained in that interval. So since 0 is contained in that interval, right? We do not have a concrete evidence of a difference between those two. So in doing the Marasculio test, you're going to do pairwise comparisons. You're going to calculate a margin of error using the chi-square value distribution, and then you're going to calculate the absolute value of the difference between the sample proportions, and you'll compare those two. And if your point estimate or the absolute difference is larger than the margin of error, we will conclude that there's a difference between those two proportions. If it's not, we will say that we don't have evidence of a difference between those. So that's essentially what you do with that test. All right. So going to my spreadsheet, this, as you could see, is the formula right here. They refer to this part, the margin of error, as a critical value. So each pair will have its own critical value. So CVIJ, and that's based on comparing the sample proportion from sample I and sample J. So I've actually set it up here for you with this particular problem that we were doing earlier. We had 4 countries, right? We had UK, China, Russia, and United States. If I label them A, B, C, D, then when I go here and to do the pairwise comparison, A versus B is basically UK versus China, UK versus Russia, UK versus the US. So you do all the pairwise comparisons, and then you do the missing ones. China versus Russia, China versus the US, and then Russia versus the US. So there's 6 comparisons to do when you have 4 different countries. So here's the sample proportions, right? And that's based on the data. If you actually go back to the data, so the sample proportions for each one of them in terms of the proportion of users, you go to the observed frequency. So it is 480 over 800, right? 215 over 500, 343 over 700, and 640 over 1000. So those are the based on the observed frequencies, those are the sample proportions of internet users. So if you were to go back to this, we're using those values right there: 6%, 60%, 49%, 43%, and so forth. All right. So, given those sample proportions, and then I really should have just demonstrated what these proportions are. So I could actually put them here for you, so you could see calculations. So sample proportions. And so that would just be the 480 divided by the 800.6. And if I just spread that, then we're looking good. All right. I'm going to increase the size. There you go. So essentially 60%, 43%, 49%, and 64%. So going here, we will do the pairwise comparisons. And so if I take UK versus China, so it would be 0.6 versus 0.43. Here's the absolute difference. So you simply just take the difference and you say absolute. So there's a function called ABS, absolute difference. What's the sample size? 800. Sample size for China is 500. And then I calculate the critical value using this function right here. All right. Now, to get the chi-squared value that you're going to use, I've already determined it here. 7.815 is the very same critical value that we use in the first part of the question, 7.815. Right? And then the difference. Now I'm going to compare whether or not the sample difference, the point estimate, is greater than the critical value. As you can see, 0.17 is larger than 0.079, which is the critical value, and that's comparing the UK and China. So clearly there's a difference between the UK and China in this particular case. There's a little function that Excel allows you to do, which is to say, if this value is greater than this value, put yes. If it is not, then put a no. And so that function is actually in there. All right. And we just repeat the tests, and then here are all of our situations. So clearly there's a difference between the UK and Russia and the UK and China. Between the UK and the US, we don't find a significant difference. That's because if you look at the samples, 60% in the UK, 64% in the US. These are not terribly far apart. Then China and Russia, 43% and 49%, not terribly far apart either. But China and the US, we're comparing 43% to 64%, we definitely would conclude that there's a difference. And in Russia and the US, 49% to 64%, we are satisfied that there is a difference between those. So that's the pairwise comparison between those. If you have a different problem and you want to use that template, all right, so it could be that you have only 3 populations or 4 or 5, whatever it is, just create the combinations. And any ones that are missing, then you would have to just add them in. So if you have, for example, had 5 that you labeled from A to E, so you'd have to go A versus B, A versus C, A versus D, A versus E, then B versus C, B versus D, B versus E, and so on. You would have to do all of those to make sure that you cover all of the you'd have to do all of those to make sure that you cover all of the options in doing that. All right, so use the template, modify it to suit what you need, and then you could actually do the calculation. It will be faster. So particularly in the tests, rather than trying to do all these hand calculations, you could take advantage of the spreadsheet, edit it. Hopefully you're good enough with Excel to just edit it, and then use it to give you the information that you're looking for. All right, good. So that was the comparison, or I should say comparison, but testing for the whether or not there is equality of population proportions. The second one, test of independence. So this is a case where we wanted to know if I'm going to switch over to here. This is a case where we want to know if there was a relationship between the type of company and the employment plan that the company is planning on putting on. So these are the observed frequencies. For 37 private companies will add employees, 19 companies will not have a change, 16 private companies will lay off, 32 public companies will add employees, and so on. So here are observed frequencies. Now I had it set up for 4, but instead of the 4, we're only using 2 columns in this case, right? So 2 types. So I just have it generically as name, and then I put 0 values in here because I don't have any values. In fact, what I did was I took the template from over here when I did my equality proportions and I expanded it. I sort of edited it to give me this template right here, right? So what's missing really are the rest of the other 2 countries that we had before. So I have just replaced them with name. So if you have a problem that has 3 columns, then just put the appropriate names in there. 4 columns, put the appropriate names. 5, then you're going to have to add a column to the template. Okay. And then of course you may have to add rows or just ignore rows if you don't have the same number of rows. So there for 1, 2, 3, there are basically 3 rows and 2 columns in this particular setup, but you could add rows and add columns as you need to. So the same idea here, that the formula that we're using to calculate the expected frequencies is still the same: row total, column total divided by the overall sample size. So as you could see here, I have zeros in here, but my totals are fine. And then when it comes to calculating the chi-squared values, notice that what I did was I deleted, because I would have infinity in here for those values that are 0. If I just drag that across, you will see what I mean. I get infinity and it messes things up. So all I did was just deleted those because I don't need them. And here I have my values. So now I have my chi-squared test statistic as 9.44. Here's my significance level, my number of rows, my number of columns, my degrees of freedom, and I will get my critical value based on that information. And then here's the p-value based on this test statistic of 9.44. As you can see that the p-value is less than 5%, so I would reject the null hypothesis. So I could actually set this up where, let me see if so decision, so this would be if my p-value, right, so I need to put an equal sign, equal if, oh, sorry, there's an error here. Let me make it bigger so that way you could see. So if my p-value I need to do this again, sorry. Increase the size of that cell so you could see better. Alright, so if I need to put equal because the function if, there we go. So if my p-value, which is here, is less than or equal to my alpha value, comma, then I would say reject comma, do not reject HO. Okay, let's see if that works. So there you go. Reject HL. Sometimes you could actually set it up to be a, you could set it up to be, how do you call it? A color, if you want to. Red for reject, green for don't reject, or something like that. So here it is right here. That's my decision. I'm just going to shade it something different. Green. No, that is the text. Sorry. Let's shade that green. Something different. Okay, so this is cool. And so here we go. And then last but not least, if we're doing our goodness of fit test, the goodness of fit test, I've sort of, because it's really not set up as a matrix per se, but really just a one row problem. We don't have to actually use a matrix structure, so I've changed the structure just a little bit. So this is a case where with testing of goodness of fit test, or was what we call this, goodness of fit test. With the goodness of fit test, what we're looking at is a situation where you hypothesize a distribution, and then you take a sample and you see if the breakdown of that sample is consistent with that distribution. So as I mentioned just to give you an example, let's say if I were to give you a distribution where I say I think 30% of students will get an A in statistics, 40% gets a B, another 20% gets a C, right? So what's that? Let me see, 30 and 40, 70, and 20, 90, and then 10% gets essentially a D or F, right? So if I use that, then I should expect to see that kind of breakdown in a sample. So if I took 100 students, I expect to see, say, 100 of them, 100 students, 30 of them getting an A, 40 of them getting a B, 20 of them getting a C, and then 10% of them getting a D or an F, all right? So that's what I should see. That's my expected frequency. But when I take the random sample, I may see something very different. And so it could be that, so I need to actually test, is the distribution that I actually gave a good fit? So here's the hypothesized distribution, and that actually comes from your problem data right here. In this particular case, it was all 20%. You had 5 categories of companies, and they all are supposed to be divided in terms of 20%, 20%, 20%, 20%, right? And however, out of a sample of 60, this is the breakdown that we saw. 5 of them were in category A, 8 of them were in category B, 15 of them were in category C, and so on. Now, if the hypothesized distribution is correct, then with 20% in each category, then if you break down the 60, right, using the 20%, each of these categories should have 12, right? 2.2 times 60 is 12. So you should have 12 in each category, because for this hypothesized proportion distribution, all of the categories have the same probability. It doesn't have to be like that in all cases. That's just this particular situation. And you can see, so that would be our expected frequencies over here. This would be our observed, and we simply use the chi-squared formula. So observed minus expected squared over the expected will give us these values right here. And we just simply add them up. Our test statistic right now is 11. Let's make that green. Okay, different color, because we already have green. Make it yellow. So 11.5 is the value of our test statistic, right? And we could essentially take, I need to do that. I'm going to copy this. I should have done it ahead of time. I just realized I hadn't done it. But that's okay, then you get to see me do it. Okay. So significance level is this. How many rows do I have? Actually, I don't have any. I just have one row, one column. There's 5 columns essentially, but just one row. But for this, our degrees of freedom will just be given by the number of categories that we have minus 1. So in this case, it was 5 minus, so that would just be 4. I'm going to actually put it in, as opposed to using a formula. So there's this, essentially 5 categories. So we could call these categories, just to be consistent in this case. We don't really have rows as such, but if we lay it out in terms of a row, then there's just only one row. Let's just leave it as one row, but we're not going to use that in the calculation. The degrees of freedom would be equal to, just to make it a function, the number of categories, right, minus 1. So that's k minus 1. All right. So we have this information right here. Our critical value, let's make sure that we're doing that correctly, is 9.48. So we would have the inverse, right? So C13, which gives us, yes, that's our alpha value, and this value right here, our degrees of freedom, C16. So that's our critical value right here. Our p-value, we need to now take the degrees of freedom, and so we have F. It's F. What's this row here? I think it's F9. So it's F. So it's 9. So we have F9. So we need to change in that function F9. F9, and the degrees of freedom is still C16. So there we go. There's our p-value right here. So we do now our comparison. So since the p-value is smaller than alpha, we will reject the null hypothesis. So our value is actually correct. If I change this to 1%, 0.01 at a 1% significance level, you notice that it actually changed to do not reject HR. So it's working fine according to this. Very good. And here we go. So that template is actually there for you if you are doing a problem involving the goodness of fit tests. And so that's the free templates explained, and hopefully you'll take advantage of that and use it in working some of the sample problems. If you have a need for it during the test, have it set up and ready to go and make the changes. If you think you could do it faster on your calculator, go for it, whichever one works for you. All right. If you're fortunate enough and the number of rows and columns are identical to that, then just substitute and voila, you get all of your answers with you. Okay, so hopefully this was helpful. Talk to you soon. Bye-bye.